Okay, so for part 1 of homework 2-3 here, we'll hopefully again get through maybe the first half or so of this. Right? So while an object or a projectile is in the air, with upward being defined as positive with no air resistance, which of the following is true? We know the horizontal component of velocity does remain constant. However, the horizontal component of the acceleration is not negative g, right? If it had a horizontal acceleration, it wouldn't be constant velocity. So again, horizontal component of the velocity remains constant. That is true. And the vertical component of its acceleration is negative g. Well, since we've defined upward as being positive and we know gravity pulls downward, this is my correct answer. Right, so if you read the rest of the way through the other options here, you would hopefully agree that B is the only option that's correct. Right, the vertical component of the acceleration is not zero. The vertical component of both the velocity and the acceleration do not remain constant, so those two are out. And then the vertical component of the velocity remains constant again. I can rule that one out. Okay, so hopefully question 1 wasn't too bad for us, right? Question 2, similarly, is a good one to think about, but hopefully not terribly difficult. For general projectile motion, when the projectile is at the highest point, right, what do we know about it? Well, the acceleration is definitely not zero. Watch out for that one, right? The velocity could be at zero at that point if it's thrown straight up. The velocity is perpendicular to the acceleration. Well, that one is definitely true, right? If it has velocity at the top of the path, we know that velocity would be horizontal and the acceleration would be pulling straight down, which would be perpendicular to our motion. So that is the option that is true for this one. Again, the velocity and the acceleration are both zero. No, it would just stick up in the air, which would be weird. The horizontal component of the velocity is zero. Not necessarily, right? If I'm throwing it off at the angle, that would not be true. That would only be true if I threw it straight up. And then finally, the horizontal and vertical components of velocity are both zero. Again, that would only be if we threw something straight up, but then it wouldn't really be considered a projectile if I threw it straight up. So option B is definitely my best choice for question 2. So then moving on to question 3. Alice and Tom dive from an overhang into the lake below. Tom simply jumps straight down, he drops straight down, whereas Alice takes a running start and jumps off with a horizontal velocity of 25 meters per second. Neither one experiences significant air resistance just as they reach the lake below. Which of these is true of their speed? So notice all of these are indicating their speed. So the speed of Alice is larger than that of Tom. The splashdown speed of Alice is larger than that of Tom. They will both have the same speed. The speed of Tom will always be 9.8 meters faster than Alice's, and then finally down here. Right, well, if Tom is just jumping, he's just dropping straight down, and then Alice, on the other hand, is running off the cliff, and she's striking down somewhere over here, we know that Alice would have both a horizontal and a vertical component to her velocity, whereas Tom would just have a vertical. And more importantly, we know that their vertical components would be the same, so Alice definitely has a higher speed, and so the speed of Alice is in fact larger than that of Tom. That is true. So if we look at that information, now the splashdown speed of Alice is larger than that of Tom. What that's actually trying to say is the downward directed speed, right? But they'd have the same vertical component of their velocity, so that one's actually not true. They will both have the same speed again. Alice has a horizontal component, whereas Tom doesn't, so that's false. The speed of Tom will always be 9.8 meters per second larger than Alice. We know he's moving slower, so that's definitely false. And the 9.8 should just tip us off. They're trying to mess with us with gravity, right? And then finally, the speed of Alice will always be 25 meters per second larger than Tom. Do be careful with that one, right? She's moving at 25 meters per second horizontally, so let's say hypothetically they were both going 10 meters per second downward, right? The resultant of her speed here would not be 35, so she wouldn't be moving 25 meters per second faster than Tom. So again, this one's trying to mess with you a little bit, but because we're adding them as vectors, and to add them as vectors we have to do the Pythagorean theorem, it's not just 25 more than Tom's. So it is option A is the best choice for that one. Right, so I took time to break all those down, but hopefully you guys all agree. Not too bad. Okay, so question 4 here, obviously a very convoluted question for a relatively simple context, but I had to have some fun as I wrote this, right? So anyway, you've got a monkey in a tree up there. It's 20 meters above the ground. This was the type of question we saw in class, right? If we're trying to aim and fire something at the monkey, should we aim above it, below it, or directly at it? Well, the key here is even if we're standing on the ground and the monkey is in the tree, right, as the monkey falls when we release it, well, both objects are going to accelerate downward at the same rate, and both objects are going to fall downward at that same displacement of 1/2 at squared, right? this tells me how much the acceleration affects the displacement. So because they both release at the exact same moment in time, they both fall the exact same amount based on the acceleration. And therefore we want to aim directly at the monkey, right? So again, on a problem like this, that's a big concept. The reason for that, again, in the absence of air resistance, both objects fall down the same rate due to the acceleration. So hopefully this first part of question 4 was not too bad. So a follow-up to question 4, right, this part B of the same question, I went ahead and wrote down the correct answer, so if you are confident you got that right, feel free to jump ahead in the video. But for those of us that weren't comfortable with this, obviously I'll break it up. So it says she fires standing 10 meters from the base of the tree and launching the food at a speed of 33.5 meters per second. What height does the food reach Zinni as he falls? So anyway, I've got my tree, right? I've got my tree that's 20 meters tall. It's got to be a tree, so I'll make it a happy little tree here. You guys probably have no idea what I'm referencing, but whatever. So I'm standing 10 meters away, or Ashton is standing 10 meters away, right? The height of the tree here is 20 meters, and we're firing, we know based on my last answer there, that I'm firing directly at the monkey. So I'm firing at that angle, which is very important, because I know the velocity that I'm firing with, right, 33.5 meters per second. And so if I know the velocity, I want to use the angle to help me find the components. So all I'm going to do is, based on the distances, I'm going to set up a little trig, right, to find my angle. So the tangent would equal 20 over 10. So then tangent inverse of both sides, and I get my angle, my theta, equal to 63.4 degrees. Okay, so that tells me the theta involved here. So then again, the reason that's helpful is now I can find my horizontal and my vertical components of the velocity. Well, the horizontal component would be 33.5 times, because it's the adjacent leg, cosine of 63.4, right? So then calculating that number, I get that to be about 15.0 meters per second. And I could find the vertical component as well, although I actually don't even need it. And we'll look at why here in just a second. Okay, so at this point, the reason I found my horizontal component was I know how far she is away from the tree, right? I know she's horizontally a distance of 10 meters away from the tree. So what that helps me find is the time that it takes for the food to reach that horizontal position, right? We know that in actuality, the food is going to launch up, but then it's going to fall a little bit as it goes there. But it still has to travel 10 meters horizontally, and it's moving 15 meters per second. So if I use the only equation I ever need, right, for my horizontal moment, or motion as long as there's no acceleration, so I'm using 15 equals 10 over t, and then solving for t, obviously would be 10 over 15, or 2/3. Obviously you could call that 0.66, 0.67, whatever you want to do with that. I'm going to go ahead and leave that exactly as 2/3, just so I don't have to round it, and because I can do that in my head without too much trouble, right? I know I could do 0.66 repeating as well, but never mind. Anyway, the question wants us to know what the height the food reaches Kenny at, right? I mean Zinni, not Kenny. Anyway, I want to know what height the food reaches the monkey. So I want to figure out how far the monkey has fallen during this period of time, because we know that's when the food will make it over to the tree. So it's that same period of time that the monkey is falling for. And so if I look at my vertical measurements, right, just the same way we normally would, I know the initial vertical velocity of the monkey. I really don't care about the food anymore. I'm just looking at the monkey. His initial vertical velocity was 0 because he's just dropping. I know the acceleration is 9.8, and I now know that the time is 2/3 of a second. So if I want to find my change in height, my change in y, I'm just using v sub 0t plus 1/2 at squared, right? I'm using my position as a function of time. So I'm looking for that change in height. I know the initial velocity is 0, which simplifies that a little bit. And then I have 1/2 times 9.8 times 2/3 squared, right? And then all I have to do is calculate this. So my change in height ends up being about 2.18 meters, right? So then 2.18 meters, that represents how far the monkey has fallen during this period of time. So coming back to my actual answer, all I did was I took the height of the tree, which was 20 meters, minus the 2.18 meters that the monkey has fallen, and that's where I got my 17.82 meters above the ground. Okay, so anyway, not even quite a system of equations. You definitely could have set up a system of equations for this, but because I have a means to directly find my time, all I really need to do is use the horizontal piece to find my time, and then use the time to find out how far it's fallen. So hopefully not a terrible question, although I can see maybe having some difficulty getting started. Obviously, if you do have any further questions on this one, don't hesitate to let me know. And then finally, question 5, probably be the last one we get through in this first part. We may be able to get a little bit past that, but again, if you've got this 44.3 meters per second, you're welcome to jump ahead in the video here, but probably this will be the last question I cover in this first part. Okay, so we've got a catapult. They tabulate the results, so all that's just background, right? The range of it is 0.2 kilometers. Okay, so it's starting here, it goes up, it goes over 0.2 kilometers, which is in terms of meters, right? Which is what I'm going to go ahead and convert it to. That's 200 meters. It does tell us that the angle of launch is pi over 4. We do need to be comfortable enough with our unit circle to realize that pi over 4 is 45 degrees, right? So we do need to be comfortable with that relationship. If that's one you're not comfortable with, let me know and we'll work on that a little bit more. But we do need to have that down. And then finally, the landing height equals the launch height, which I've already represented in my picture. I know that it returns to the same elevation from which it was launched, which is very important, right, as I set this up. Okay, so they want us to know what the initial velocity of the launch was. Okay, well, I know the angle is 45 degrees, and I know the total distance was 200, but that's about it, right? That's about all I know. So the key to this question is then setting up both components, and this one we actually will have to create a system of equations. Okay, so for starters, I'm going to go ahead and define this initial velocity as v. I don't know that measurement, nor do I know the components, but I can represent the components in terms of v, right? My horizontal component would be v times cosine of theta. My vertical component would be v times sine of theta. Okay, so nothing too crazy here. All I'm doing is breaking it up in terms of the magnitude, the hypotenuse. Right, so I've got those two to work with. Well, let's start then with our horizontal piece of the motion. I know the only equation I need horizontally is Vx equals delta x over t. I don't know how long it took. I can represent Vx in terms of cosine, so v times cosine of 45. And I know the distance, right? I know the distance is 200 meters. Okay, so at this point I get stuck though because I have both the velocity and the time which are unknown. Okay, so I get stuck. When we get stuck, obviously that's when we take a step back and we start doing our vertical measurements, right? So maybe vertically I'll have enough to know. So vertically speaking, I know my initial velocity is v times sine of 45 degrees. I know my acceleration obviously is negative 9.8. Which I am going to go ahead and define this as negative since it's going down, and I've defined this as positive for going up. And then here's the next tricky part. So I don't know the time, I'll again just call that t. The next tricky part is what I want to do with my final velocity. Now I could either make my final velocity the final velocity at the top, and then I would just have to remember to double this time so that I could relate it to that. So if I made my final velocity of 0, the time would actually then be 1/2 t, because it only takes half the time to reach the top. But actually what I'm going to do instead, because I think it's a little bit easier, I'm going to go ahead and define my final vertical velocity. When it hits the ground over here, I know it's going to be the same magnitude, but the opposite direction. So I'm going to define my final vertical velocity as negative v times sine of 45. So then what that allows me to do is when I set up my vertical components here, when I set up my VOTAT for the vertical measurements, I can then set this up as negative v sine of 45 equals positive v sine of 45 minus 9.8 t. So again, if I look through here, hopefully it's starting to jump out already. The only variables I have are v and t. So maybe at this point, if you want to try to finish solving it out on your own, feel free to pause and then come back to this if you do get stuck again. Right? But at this point, all I need to do is then substitute v or t in. The other thing that I'm the other thing I'm going to do to make this one a little bit easier, I'm going to go ahead and solve the second equation and get the negative 9.8 t by itself. So I'm actually going to go ahead and plug, subtract this over. Right? So if I subtract that over, I actually get negative 2v sine of 45 equals negative 9.8 t, right? And then I can make those both positive. The reason I'm doing that though is I actually know, going back to this original equation, sine of 45 and cosine of 45 are the exact same thing. So I actually know my v of x and v of y are equal. And because of that, I can substitute this whole thing in down here. So I get 2 times 200 over t, and then 9.8 over t, and then just solve for t and plug that back in. I'll go ahead and finish this in part 2.